I'm Pete Zelinski. This is the SLS Mindset, a series of videos on realizing the full promise of selective laser sintering additive manufacturing for producing repeatable, rugged polymer parts. I am at Lifestyle Additive Manufacturing, a specialist in SLS. I'm with Operations Director Nate Stevens.
Hello.
Hello. Strength is another advantage of SLS. SLS can produce strong polymer parts. Design choices can optimize that strength, but strength is a broad term. So let's get more specific. When a product designer comes to you and says they need a strong part, what are they typically talking about?
Well, my first question is always, where do you need it to be strong? What's the application? Strength is a very relative term. We have, the ultimate strength, how flexible the part is, how rigid the part is. Both are things we need to think about. We have some ribs in here that are the primary support for this part. The thin sheet of plastic on the outside gave it that strength that we needed in that direction. And so he was able to both design for cost savings as well as for strength. SLS gives you the opportunity to optimize in more than one way.
This web of material, it's really thin, and yet to machine a detail that thin would be very challenging.
Especially in polymer and injection molding, you wouldn't really be able to injection mold this very well because the thin parts will cool faster and you'll get weird warping, whereas SLS printing gives us all of the strength in the areas that we want it and savings in the areas where we don't need it.
The strength of a part, what types of strength are you most often asked to deal with? Is it ultimate strength, impact strength, fatigue strength?
It's all of the above. And this is a good example where we added material in areas that we needed it to be more rigid. This is another part that we needed the part to be fairly rigid, but they wanted this little spring in here. We've had parts that needed to be really rigid. We've had parts that need to be optimized for weight savings with clever latticing and design work. It comes down to understanding the material properties. Thicker walls behave this way, thinner walls behave this way.
So these parts are made of PA12 nylon. How does the ruggedness of this material when it's printed compare with the same material when it's molded?
After printing and vapor smoothing, these perform very similar to an injection molded part. Because of the SLS process, everything is a solid infill, solid plastic all the way through, and that allows you to add material where you want it to be more rigid and remove material where you want it to be more flexible.
Is the strength isotropic? Is it the same in XY as it is in YZ?
Not necessarily. The layer lines will always be somewhat of a failure point, but in this PA12, I've seen minimal differences at best in the Z direction.
When you are designing to achieve strength, does that affect part orientation choices?
Sometimes, yes. Something like this, I would orient it like this because it gives us the most consistent properties along the beams here. If I did it like this, then now all of these beams have the layer lines. If we're trying to maximize the strength, I'm always thinking about orientation. You always have a fault along the layer line. When you're printing parts in FDM, like a desktop printer, there is probably like a 50% drop off in strength in that layer, whereas this is maybe 10% drop off in that layer. You get better properties from the Z orientation from SLS than you do in other printing processes.
Does post-processing have an influence on the strength of the part?
The biggest post-processing step, the vapor smoothing. It really gives a uniform sealing of all of the layer lines where most of the forces are experienced. The part becomes a very uniform isotropic part.
So have there been components where vapor smoothing got you over the line?
Yeah, weirdly, spring features like this are where I notice it the most. That sealing of that outer surface of the material gives it that flexibility, that improved strength.
Are there types of components where the strength that can be attained through SLS makes additive manufacturing a candidate for that type of part?
Springs and clips are great examples. You're always limited by where is the layer line. With SLS, a similar mechanical performance, no matter how you print it, and especially with the vapor smoothing, it'd be a very resilient part.
This locking mechanism.
Yeah, this was for a test fixture. We printed our own plunger surface. We actually printed these parts flat like this, trying to get the most strength. It was a very stiff spring. Even the tracks that these little nubs ride in, you couldn't print any other way. Feel how much pressure those little nubs are under at all times, but they hold on.
So SLS, a fine detail process, and here's an application where both strength and the fine detail were important.
These were actually two separate parts, aluminum, and this inner part was machined in plastic. With SLS printing, we were able to combine them both, accomplishing cost savings, precision detail, all the strength properties that we needed out of it. We were able to add the material where we needed it, remove the material where we needed it, and we were able to accomplish uniform material properties.
This episode's part of a collection on the SLS Mindset, how to design for selective laser sintering. Check out other videos in this series.